Okay, we are into it now. I told you that we never nerd out, except right now, like the next 5 minutes. Because one thing we need to understand is just this principle of diffusion. Now, I will never ask you a trick question. So when I ask you this clear glass of water with blue food coloring, in another minute, what color will all the water be? What's the answer? Blue, right? That's diffusion. You have the high concentration of blue food coloring spreading out until it's evenly distributed to areas of low concentration. The same thing happens in a building. We open the front door, it's hot outside, it's cold inside, cool inside. You open the door from the outside and you get that blast of cold air, right? And on the inside, they're like, dude, close the door, right? They're getting the blast of warm air. Those forces try to equalize. So that happens with air, it happens with temperature. And then along with air, we have humidity, so vapor. If it's humid outside, that high concentration of humidity is going to try to force its way through the walls until it equalizes with the inside of the building. Indoor air quality, the same. If you've been somewhere where there's forest fires, you're suddenly very aware of like how your air barrier stops smoke and things like that because you can smell it. Same thing, high concentration on the outside of a building working its way in. Can go the other way. You can have high humidity inside, low humidity outside, and it's going to just try to equalize. So that's diffusion, and that's the force our buildings are working against, and that's why we put in barriers. So all of these barriers are meant to slow down or stop that diffusion. So this is a good thing to write down, the 4 barriers. Air's got indoor air quality moving with it. It's got temperature. Occupant comfort, big part of what the air barrier helps with. Water's the one exception. It's not really a diffusion thing because as a liquid, it's like a solid, like it goes through or it doesn't. But vapor, definitely diffusion. And then thermal, hot outside, trying to equalize. We live that all the time. It's trying to equalize those temperatures. So usually it's one product on the wall. It's a sheet good, it's a peel and stick, it's a fluid applied that's going to give us the air barrier. It's going to stop the water. It's going to slow the vapor transmission. It's one product that does all of that. I will, throughout the training, call that an air barrier, but there's lots of names for it. Air barrier, water barrier, weather barrier, air vapor barrier, just vapor barrier, air water barrier, or AWB, or AVB, like lots of names. And every architect chooses something different. I use air barrier because like we get it that water needs to be kept out. If I say water barrier, like everybody understands we're keeping water out of the building. Many of us forget about the air barrier. And since temperature and humidity and air quality all move with the air, I just choose to use the word air barrier. Most of the big issues on projects where they're done and then there's complaints are about occupant comfort. You know, they've got some spot of the building that's really hot or gets really cold, and then we open it up and it turns out the air barrier's not intact and there's water damage, but it started with occupant comfort. So I'll say air barrier, but there's no right or wrong when we're talking about what that barrier is on the outside. Who's worked with Tyvek before, this stuff, or maybe seen it? It's like the big Home Depot, right? Is this a really good product, or it's kind of the bottom of the barrel, right? Like it's the lowest performer. It's a funny story. It's not funny, it's just a story. Tyvek was the first ever air barrier. And when they released it, it means they were the first company to ever take the product, put vacuum on one side, and measure the amount of air that goes through. And that air, if you take it in vacuum and suck air through it, is 0.004 cubic feet per minute. So like cubic foot, this much. And let's watch this video real quick and I'll continue it. This is a top view of conceivable that there's a path here for oxygen to get, air to get through a little bit, yeah. In fact, 0.004 cubic feet per per minute. That's what they measured. And then vapor is the same way. So vapor molecules are H2O, of course, but they're smaller and they can make their way through. And they'll give vapor barriers, a rating on how much vapor gets through. And but once lots of vapor molecules get together, then they form a drop. Think about our clouds are vapor, then they condense, then they fall to the earth as raindrops. Same thing, so like a raindrop or a drop of water is huge, and it can't get through the Tyvek. So if you put steam underneath Tyvek, some of the vapor would come through, and then it would beat up and sit on top, and the water wouldn't go through. So people really liked Tyvek because it's highly vapor permeable. Lots of vapor can get out. If water gets in, it steams up, and it leaves the building. But when they put it in the code, everybody freaked out. They're like, they're the only air barrier, and you just put them in the code. Like, you just gave them a monopoly, and you've ruined the building industry. Well, everyone forgot that it takes us like 8 years to adopt a new building code. So by the time we really were using air barriers, there were lots of other products being made. And if Tyvek is put in the code as 0.004 as the requirement, everyone that came after made an air barrier that was better, right? Like, if that's the minimum requirement, yours is going to be at least that, but probably a little bit better. So Tyvek went from being the first to now like the code minimum worst air leakage rating that you can get. So kind of a funny life cycle there, right? But all of those products, all those ratings come down to, you look at them under a microscope, what kind of pathways do they have for air and vapor to get through? If I put a car tire up here, 1/4 inch of rubber, would you see any paths for air? Nothing, solid, right? Or our tires would go flat all the time. A lot of the barriers we use are rubberized asphalt, very similar. And when they're pretty thick, they're gonna have really, really low ratings for air and vapor. And so when you see these ratings, sometimes they can be a little confusing, but if you think of it as under a microscope, how many paths are there, makes a little more sense. That's why you can increase the performance by putting on 2 coats of something, right? Because you've blocked some of those paths. So that's it for the nerding out, but there is one more category of something to understand here. When you have concrete that's going to be exposed to water permanently, so podium deck, swimming pool, below grade walls where you've got soil and water, you need more than an air barrier, you need waterproofing. So a lot of times we call what's on the wall waterproofing. Totally okay. I've learned that people don't like to be corrected. But this product that goes below grade, permanent exposure to water, is waterproofing, where this stuff on the wall is air barrier or vapor barrier, whatever you choose to call it. What I found is best is to just call it by the product name, like, oh, I got Tremco here and drive it here on your project. But it's hot or cold, fluid applied, rubberized asphalt, 1/4 inch thick, 1/8 inch thick, really robust. Every once in a while, someone will come and paint air barrier over the top of waterproofing and say, well, it's not an air barrier. It's true they don't have test data for how it stops air, because it's not sold for that. It's sold to stop water. But if it's a 1/4 inch thick rubber, is it going to stop all the air? Yeah, way better than something like this that goes over the top of it. So that's it on waterproofing. It'll come up a couple other times. But again, nobody loves to be corrected, I've learned. All right, the next thing we're going to do is we're getting into rain suits. So it'll be 1 volunteer per table. We have a ton of fun with this. We've lowered down, it's like the gauntlet in the back here. It's a spray rack. We'll get that fired up. It sprays 8 inches of rain per hour, or 5 gallons per square foot per hour. That's the most that's ever been recorded in the United States. So that's actually the same rating that gets used when your windows are tested on your project. So when you're like, this test doesn't seem fair, yeah, you're right. We'll get to talk about testing, but that's the spray rack. That's what we'll go through. We're an accredited testing laboratory, so all of our stuff is calibrated. We build it ourselves. We'll take at least 1 volunteer. I've got prizes for you. You can have more than 1. It's totally fine. Nobody's ever gotten wet doing this. 1 guy got wet, but he was doing like this like chicken dance thing, and then he got like low, 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 but he like turned his back to it when he got low. So don't do that and you'll be fine. I'll show you what it looks like here. Actually, we'll get started at the beginning of the video. We're gonna have one person from each table, but the rest of you, like, I get it. You're grateful that you don't have to be in the suit. It is your job to make sure that they stay dry and have a good rest of the day. Okay, so you're gonna help them get in their suit, help them with the boots, help them with the mask. And then when people are ready, we're gonna move over here and send them through the spray rack, and it ends up looking like this. We have a good time with it. Aaron, our videographer, finds a way to make people with no dance moves still look pretty cool. Although he hasn't done that for me yet. We have our rain suits back here. One per table. They're gonna help you with the rain boots and the suit. They're different sizes. And then we'll get you ready and we'll go back to the spray rack. So here we go. Don't all go at once. One per table.